Hello everyone, welcome back to another live stream. So, this is gonna be the second part of the neural network framework that we had started to build. Now, I did do work off stream, and there was a reason for that. The main reason being I didn't know how long it would take me, and so I just decided to do this stuff off stream. I added the backward pass for the dense layer. This I just copied from neural networks from scratch, and then I added the flatten layer. This I did by myself. So I was super proud of this one. Basically, what flatten layer does is it takes a multi-dimensional input, collapses it into a single dimension. So I just did it very easily. It just took me. I just get the inputs, copied them over here, and then you just pass in the flatten parameter of numpy, return it, and in the backward pass you just return the copy. So it's super simple stuff, nothing too crazy. I added the backward pass for the ReLU. I added another activation function called the sign activation function. It just returns the signed value, nothing too crazy. I added tanh, as you can see, and I also added sigmoid, and I did backward pass of softmax. The reason why I did backward pass of softmax because I initially managed to figure it out. However, the code was getting a little crazy because you basically have to calculate the derivative of a matrix, so you kind of calculate the derivative of every single element, and so it was getting a little like for loop intensive. So I actually ended up copying this from like a web page. Now the thing was, like I did kind of sort of hack together a bit of an implementation, but it was super slow, and so I figured out, like not I, but that basically that web page used this thing called Numba. I don't know how it's pronounced, but basically you use the JIT, which I think stands for the just in time compiler or just in time, and you use JIT and you just pass in the JIT fast math equals true parameter, and then you just do all of your calculations in the so you decorate the backward pass with that. So this gives you faster execution speeds. Now, however, there's one issue that uh, basically I don't know why, but this throws me some sort of a warning, which is like it's a deprecation warning. But I really don't care about that because I'm not going to be updating my number version, so that's not a big issue for me. So that's the softmax activation function. We have sigmoid, we have tanh. So as you can see, I did do a significant amount of work off camera. However, it's pretty good still, not a big issue. So in this video, this stream, my aim is to implement forward and backward pass for the categorical entropy loss function. Loss functions, if you don't know what they are, you can just go ahead and look them up. I'm not gonna explain you what a loss function is. I'm just gonna start with the code because I mean, if I do start doing that, then it's gonna take me a long time. So let's get started. So I'm just gonna say categorical cross entropy loss. So we can just say class categorical cross entropy, and now we just need to implement the equation for it, which I just so it's I think it's like the negative log or something. I kind of forgot the equations. I'm just gonna Google it up. uh, Categorical cross entropy loss uh, equation. We also need to calculate its derivative. Alright. Okay, come on. Why isn't the page loading up? So let's just get the. So we need to get the actual equation. There we go. So it's y1 to y output size. I think this is not the one that I want to look at. Was it sparse categorical or categorical? Let's have a look. So I want to look at the equation. Yeah, this is the one that I think I want to have. Cool names when I started, blah 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 blah. Cross entropy. Alright, I think this is the one. So I do know it's negative log something. I just don't remember the equation for it. And I don't want to open up an NFS right now, neural nets from scratch. So we just need to get the equation for it. I know how to implement it. It's obviously going to be super simple. Won't be that complex because it's just math. Cross entropy, loss function. Let's have a look. This one. Towards data science is a good source. I think I can look. As you can see, I have been working on this for a couple of hours at this point. It took me a little bit of time because I actually did a lot of the stuff by myself, which I didn't expect I would be able to do, but yeah. So now we gotta do the probability. We don't want to do that. I'm not dealing with entropy. Yeah, I think this is the one. No, no, no. Cross entropy. I mean, this is not the one. All right, you know what? We can implement We can implement cross entropy or logarithmic. So, all right, we can just call it log loss. All right, let's just do log loss first. So let's do log loss first, and then we can do other ones. Because we obviously gotta implement all of them. So order doesn't really matter. Alright, so what does the equation look like? So it's alright, so Ti is the truth label and Pi is the softmax probability for the ith class. So super simple thing, nothing that complex. So we can just define the forward pass, self, and now this one will take a couple of other different parameters. So this will take the truth label and the expectation value. So we can say uh, probability and truth, not true value. And then we can just return, actually, you know what, I'm going to store it in a variable output, and we can just do np dot sum. Oh, it's negative np dot sum, so we can just do that, np dot sum, and we have to do, alright, it's for n classes. So alright, I got it. So we just do what is it, we have the true val and we multiply it with the np dot log of the probability you know what, I'm just gonna copy it. I'm pretty sure I'm gonna make like a spelling mistake, so we can just go ahead and copy this. Oops, do that. And I think we can just go ahead and return the output, and I think that's it. Actually, I don't think that's it, right? Because wait, let's test this out. So I just opened up, done like a IPython 3 here, and we can just test stuff out over here. So I want to check how does np.sum work. So if I have like a t, which is going to be a np dot, I'm just going to like a, and we can just have like 1 2 3 4 5. Oops, just do that, and I can just do np dot array a. Oops, why am I making so many typos today? Alright, so now it's an array, it's now a numpy array. So now if we do some a sum is equals to np dot sum a, and if we go ahead and print out the a sum, it prints out 15. So in this case, like, can we pass any parameters to this? So if we do like a and 2. Oh, okay. Oh, alright, so I think this is okay. I think we just need to do this much. I think I think this is correct. So now we need to figure out the backward pass. Now the backward pass will be something not so easy to figure out, obviously, because we've got to calculate derivatives. So calculus. I do have a calculator by my side, so in case if we do need to uh, use it, so it is a scientific calculator. So in case if we have issues, so for binary entropy, it's obviously just gonna be two. Yeah, it makes sense. So in this case, we gotta find this derivative. So now I would prefer that I write it down. I can't just look at Python code and calculate differentials. So let's use OneNote, write stuff down. Uh, Obviously, I don't know if I'm gonna be able to do this or not. I'm not good at calculus at all. So yeah. Is there like some online equation editor? Because I'm not very good at drawing with my mouse, and my iPad doesn't have any battery, so I can't exactly, uh, mirror my iPad display to my laptop right now. So in terms of like I don't know if I'm gonna have this code up on GitHub. I still haven't created like any GitHub repo, and I am planning to maybe create a GitHub repo for this. So in case if you guys want me to do something like that, do let me know. Cause I mean this code is relatively complex. Like it's not something that you would uh, look at every day. So yeah. And I've also done like tests for this stuff. When I say test, I mean I just threw together some input. I have not exactly validated it or anything. I just had like a quick test for like the flatten layer. But yeah. All right, there we go. Where is OneNote? There we go. All right. Oh, let's just go ahead and add a quick page. I'm not gonna have any titles or anything. All right, cool. So this is gonna be why is it lagging? Why is it lagging so much? Oh, come on. All right. What is the equation? Let's just have a quick look at that. It is. Oh, all right. It's negative. I don't know how I forgot that. Oops. It's negative I equals 1 to n d I log p I. All right. So what I don't get in this thing, in this one, is that how do I like go ahead and even start, like, do we have to do like this one where we actually do partial derivatives with respect for like ti and pi, or do we have to do like one derivative? Because there is no x parameter in here, so there is not going to be anything like this. I think it's going to be a two partial derivatives. So that's like the one thing wherein I'm a little confused. So let's have a look. uh, Log loss derivative. Now what's the other name? What was the other name? Cross entropy loss function. cross entropy loss derivative. Alright, let's have a look at this. Alright, so we have softmax. Softmax was, I thought it would be difficult, but I was able to do it. Alright, now which is the one that we are looking at? No, this is not the one. Is it this one? EX? No, that's not the one. And yeah, I was correct. See, we did EX with respect to OJ, and then it had EX. Oh no, it's just EX. There is indeed a mistake, blah blah blah. Yeah, but what's the. Let's look at Cora maybe. I don't know where will, because yeah, I just wanna get this one. But the cross entropy, why are we not getting the LaTeX formatting which we should be getting? Can evaluate without worrying about a function is connected to. Yeah, but I don't care. But the thing is, wait, so in this one they gave like a different equation for the cross entropy loss. It's np dot some true value and logged out probability. Differentiate. Oh, all right. So all right, yeah. So this is the function that I was actually talking about. This one. So I think it's the same thing. So yeah, it's yi. Yeah, so I think we can just do y times. Uh, yeah, so is y hat the, and y hat is the actual output as a probability where y belongs to 1 0. All right. So we can just do y and y hat just to keep it a little more mathematical, and we can just say y hat true value, actually actual value sounds better, actual value, and y predicted value. So it should be alright. Now this doesn't make any sense, because in the article we were having the probability in the log. In this one we are having the true value in the log. That is obviously two entirely different activation functions. I'm sorry, loss functions. Also, I think I can just rename it if it is cross entropy. Cross entropy. So I mean, alright, so let's just go with the one that they have shown here. I mean, not a big issue. You can have y, just add y in there, multiplied by y hat. Alright, with chain rule, backpropagation, or automatic differentiation. Oh, alright. Oh, okay. Kinda get it. First apply the inverse log, which is the natural exponential. Log is equal to natural log. Wait a second. This doesn't make any sense. Is this log to the base 10 or is it ln? Ln to the base z? Yeah, but see, there's the thing. Here he has written e to the y equals x. So this basically stands for log of x to the base e is equals to y, which means ln x is equals to y. So in this case, I think should I go np dot log or np dot ln, if ln is actually a function? Because so if we do log, the default value should be 10, right? So if we have log and the default value will be 10, that just gives us a whole different answer. And even right here where we will be setting it equal to x, see, that's the thing. Alright, so I'm gonna open up a book which will help me out with this. So the book that I'm gonna open up, I'm just gonna kind of show it to you guys over here on the screen. It is this one, Mathematics of Machine Learning. This is the book that I'm talking about. And because this thing, it actually has like all the math concepts which I had to revise on before I had to started to code this stuff out. And this has an entire chapter on uh, this stuff like automatic differentiation. So where is that chapter? It had like an entire thing on it. I don't know where it was. Gradients of matrices, back automatic differentiation, 138. Alright, so if you guys are following along, you can just download the PDF for free, and then you can just follow along with this. So this is on 138. So alright, so as you can see, it has this entire thing on backpropagation. As you can see, I don't know if you can see, but it's got this entire thing on backprop, and we're gonna be heavily making use of that. So here they have an entire topic on automatic differentiation, and I'm gonna be following along with automatic differentiation, and we're gonna try to figure out this by ourselves. So it turns out backpropagation is a special case of a general technique in numerical analysis called automatic differentiation. We can think of automatic differentiation as a set of techniques to numerically, in contrast to symbolically, evaluate the exact up to machine precision gradient of a function by working with intermediate variables and applying the chain rule. Makes sense. So what they're trying to tell us is, if I go ahead and do that, so I think basically what they're telling us is, if we do automatic differentiation, if it's something like dy by dx, if there's a simple graph representing the data flow from x to outputs y y with some intermediate variables a and b, if we were to compute the derivative of dy dx, we would apply the chain rule and we would obviously get dy db, db da, dA dx. That's just the same as f gx is gonna be equal to f prime gx times g prime of x. Intuitively, the forward and reverse mode differ in the order of multiplication due to associativity of matrix multiplication. We can choose between that and that. Alright. So reverse mode, because gradients are propagated backward through the graph. Reverse data flow, got it. So alright, so if you guys are following along, 5.121 stands for the back propagation, and 5.120 stands for the forward prop. Pretty sure. So would be the reverse mode, because gradients are propagated backward through the graph. I reverse to the data flow. Alright, you know what? I actually just had a good idea. I'm pretty sure I have the ebook also. So if I could just open up that same page, you guys can follow along. Ebook. Now I won't be reading it from the ebook because it actually strains my eyes a lot, and so I'm not gonna do that. I'm gonna read it from the physical copy, and just cause, yeah. So this is like 3 pages worth of information, and I at least want to try to understand it. I don't know if I will. Maybe I won't. But I at least want to give a good attempt. So let me just open this up so you guys can follow along. All right, cool. So what do we, which page is this on? It's on 141. Let me just open that page up real quick. I know it's super laggy, but sorry for that. Can't really do a lot. Yep. All right, this is 141. Oh, all right. So I think they have kind of screwed up a little bit of like. So Taylor series is there. I actually have like the Indian edition. This is like the uh, other edition. So for me, it's like, where is automatic differentiation? Where is it? All right, you know what? I'm just gonna look it up over there. Let's just look it up in the index. Um, automatic differentiation. All right, so this one is on 159. Cool. So I'm just gonna open up the page for you guys. I don't think you will have colors. All right, you guys have colors. That's good. Automatic differentiation. There it is. So I am on this one. Consider the function. All right, so you guys can read through if you want. So we have a function, root of x square plus exponential of x square plus cosine of x square plus exponential of x square from 1.5.109. So that is, what is 5.109? If we were to implement a function f on the computer, 5.109. Alright. Oh, it's the same thing. We would be able to save some computation by using intermediate variables. Oh, alright, so we can save computation time. That's good. Alright, so we set x squared to be a, b to exponential of a, c to a plus b, and alright, how? Oh, alright, okay, got it. And d to be the root of c. Oh, alright, so we got it. So that's gonna be like, uh, alright, so then we basically just set like the same thing for the other ones. Yeah, e will be cosine of c, and uh, cosine of c. Wait, cosine of c? Oh, yeah, got it. And f will be d plus c. Gotcha. This is the same kind of thinking process that occurs when applying the chain rule. Note that the preceding set of equations requires fewer operations than a direct implementation of function f as defined as in 5.109. The corresponding computation graph in figure 5.11, alright. So now you can follow this graph that they're talking about, this one. So we have x, apply the squared, a combination graph. All right, cool. I don't really understand the graph. I'm gonna try to understand the math. So let's go head on down below to the actual computation. All right, so we can directly compute the derivatives of the intermediate variables with respect to their corresponding inputs by recalling the definition of the derivative of elementary functions. We obtain the following. So we do dA dx will be, which will obviously be 2x. That's just super basic calculus. And e to the x, e to the anything is just going to be e to the anything. dc dA is going to be 1. Wait, let's look at c. What was c? A plus b. Yeah, a, it's constants. Wait a second. Oh yeah, it will be 1 because b will be 0 and c will be 1. Cool. And that will be equal to dc db. D del d del c will be uh, del d del c will be, yeah, makes sense, 1 over 2 root c, makes sense. Del e del c will be negative sine c because it was cos c, yeah, gotcha. And this one will be that. So now we look at the computation graph in figure 5.11. So that's where we use that graph. Cool. So now what they have done is they have done del f del c by working backward from the output. Oh, alright, so we work backward from the output. Kind of, I don't know why we are doing that exactly. Like, why are we working backward? I don't exactly get it, but I think it's just some sort of a law rule, something like that. So we are doing del f del c is del f del d del d del c del f del e del e del c del f del c is del f del d. Um, I just don't get what method they have used. If I can figure that out, that would be good. Alright, I think we gotta understand the graph nicely. I think the graph is something pretty key to this. So we have x. We apply the square to get the a. We have the a, and we gotta see what we are defining over here. Alright, so when we have a, we apply an exponential on the a to get a b. We add a b to an a, so that's like this line and this line to get a c. We apply a cosine and a root on c to get a d and e respectively. No, not respectively, but yeah. And then we add up d and e to get an f. So we have there. So we start from f, we head on to de, we apply the respective functions. So we have root and cos. We get back to c. So we add like the derivatives that we have already gotten in this case. Then we have the plus, and alright, gotcha. Alright, so now I understood the graph understood. Cool. So now that we have understood that, let's look at this one. By looking at the computation graph, we can compute del f by del x by working backward from the output. So when we are working backward from the output, why have we written del f by del c? That's the one thing that I am not really understanding. I understood del f by del d, but then we are doing del d by del c. Del d by del c. Yeah, that even that I understood. Alright, I understood that. Then we do del f by del e and del e by del c. Understood that. Then del f by del b. Oh, alright. Okay, I got it. I got it. Gotcha. Alright. That is tedious. That is tedious, but definitely doable. And if it is saying that it takes up less computation time, then that's just like a cherry on top. Alright, so basically you add these two to get this one with respect to this one, then you do this with a and b, and then you do the same with x. Am I right? Yeah, I am right. Cool. Alright, I did not expect to understand this. Obviously, it took me so long. I mean, I've been live for 33 minutes and I've written this much. But to be honest, it's all about understanding this stuff rather than putting it into code. Because code is gonna take me like 10 minutes. Alright, so now that we have a clear mathematical intuition, we can put it into code. So that's gonna be the cool part now. Because before we even put it into code, we actually have to understand if I understood this nicely. Hopefully I did. Now in this case, let's just consider this as log to the base e, because that's what that guy in Quora had did. And even though Quora is many a times not correct, let's try doing that. Now I'm gonna get rid of this stuff. We don't need that. This page is just gonna be dedicated towards finding this derivative. Alright, now I just have an issue. No, actually I think we can do that. So I think I'm first just gonna write it in the form he is written it in. So y hat I. So we can just do that quickly. We can just do y I times log of y hat I. Cool. So I think we can get rid of the eyes. That's like, if that's correct. And also, why has he not added the hat? you know what, we'll add the hat. So we know, so if we have log of y hat to be log to the base e of y hat to be a, so in that way e to the a is equals to y hat, but that doesn't seem right. No, that is correct. Alright, I didn't know that. So we have that, and we have that. Now that this one I'm gonna have in another color. Alright, so now we have to set a b. I think we can just have it as y. Alright, wait a second, this doesn't make any sense. This just does not make any sense. Wait, he didn't have any respect for the y's and y hats. Based off of the chain rule. Alright, this is 100%. This is not correct, right? Because this is yi. The values are going to be different, and thus there's no log in this one. It's obviously going to be different. So del y del x. This doesn't make sense. If I have the log of x, the derivative of log of x is 1 over x, right? So I think it's 1 over x. I'm not sure, but let's do 1 over x. So if we have derivative of log of x is 1 over x, so when we have this, so del y del x will be 1 over x, and what has he done here? That just doesn't make sense. So let's just look at this one. I think let's look at the book again. So see, the issue that I'm facing is that we have two variables. We have y and we have y hat. So if this was y, then this wasn't a big issue, because let's try doing it with just y rather than y hat. Maybe that will make sense. Let's try that. So if we set a as log y, and if we just do that, so we set a as log, actually no, let's not do log basic. I'm pretty sure the guy is incorrect. So and if we set b as, oh, alright, we can actually do this a lot simpler. We could just do it like this. If we set a as y, which is the actual way these guys have done it, we set b as log of a. Now that's correct. That's correct. I'm pretty sure that's correct. So we have, I'm pretty sure, taken care of this part of the equation over here. And so now what we have to do, let me just put like a little thing around here. So now let's model a graph for it. Alright, because I don't think I'll be able to do it without a graph, so let's just have a graph. So we have a y. We have a y, and then we are multiplying it in order, and actually wait, are we gonna, yeah, we are multiplying it in order to, actually we are not just multiplying it. Oh no, we are doing log. Multiplication is obvious, kinda. We are doing a log over here. We are doing a log over here in order to get a y Actually, no. Why am I saying why? This has to be A and this has to be B. I know I'm making a lot of mistakes, but I'm literally learning this with you guys. So the fact that I've even able to even managed to implement this much is very impressive for me. So if we are traveling backwards, so we have to start from B, head on to the log. Actually, no, just it's just gonna be head on to the A. This actually, I think this is relatively easy. Famous last words, but yeah. Uh, cool. So I think it will be del B by del A, and wait a second, that doesn't make sense. If there is nothing intermediate, there is no intermediate thing. Wait, am I just complicating this? Cause yeah, I'm just complicating this, right? Cause yeah, y log y. I could just do chain rule on this, right? Could I? Yeah, I could. That's just, god damn it. Alright, so if we do y log y, and if we are doing chain rule, it's gonna be f g prime x, so it's gonna be y times 1 over y if we are doing that, and it's gonna be f prime x, so that's gonna be 1 log log y. If we cut that off, we get a log y. Is that gonna be the derivative? I'm pretty sure that's not the case, but let's have a look. Wait a second. 142. Just a second. Let's open up Wolfram Alpha. I'm gonna have to verify this in some way or the other. Alright, let's implement the math input. We're gonna calculate the derivative with respect to y of y, y log y. And technically that makes sense. Alright, cool. Compute. Why is there a plus 1? Real part imagine. Holy hell. Log y plus 1. I'm just getting log y. Why is there a plus 1? Why do we have a plus 1? Why is there a plus 1? Man, I want the step-by-step solution, but that's gonna be premium. D by dy. Use the product rule. Oh yeah, I was doing. Oh god damn it. Oh yeah. I used the incorrect rule. Chain rule can't be used in this, right? Because, yep, we gotta do product rule. Uh, let's look up product rule. Differentiation product rule. It's D. Alright, so it's, if we are doing this, if it's y log y over dy, that's gonna be, so if we set u to be y and v to be log y, the answer to this is gonna be u dv dy plus v du dy. So it's gonna be y times 1 over y plus, I know, v will be log y times 1, so we get that off. So the answer is log y plus 1. Is that correct? Alright, let's hope that's correct. But what about this? This is y hat. Damn it, this is such a pain. I don't even think we're gonna be able to implement this much. Y hat focus entropy, then we have that. What is the final answer? Since we have this, we don't need to worry about this, which in this case is the derivative of this and we can't keep chain derivatives and I don't know what's up with the input node that. Cos entropy. Oh, alright, so that's the reason why so many articles merge cos entropy and softmax. Seriously. Alright, I'm gonna put this in here. We're just gonna do like cos entropy. So how do we do sum? Alright, let's have a look. Let's just go up to like 10. This is just gonna be like a sample. Assuming log is large for logarithm. You know what, let's go with this one. Derivative d by dy minus the minus 11 log y plus 1. If I make this 11 minus 12, alright, if that is the real, like, see, here's the thing, right? If this was x, now that will become a partial derivative. See, so see, that's the thing. This is such a stupid thing. Alright, now, seriously, you know what, at this point, I seriously don't know if I'm gonna be able to implement this by myself. Let's copy the code at this point. Softmax and entropy loss, Python examples. Softmax was like easier. This is just bad. Derivative of cross entropy. Let's have a look. We use cross entropy laws with softmax function as are used in the output layer extensively. Now we can use derivative of softmax that we derived earlier to derive the derivative of the cross entropy. Alright. So we have the log of pi, and then we do that, and so we get from the derivative of softmax that we got earlier. What did we? So del O by del L by del Y um, 1 minus pi. So y is a one hot encoded vector for labels. So yk is 1 and yi plus that is 1. So we have a pi minus yi. So x is the output, grad is that. It can be computed as, note that y is not a one hot encoded vector. We find the grad, we do that. If it is just pi minus yi, are you kidding me? What is m? M is the shape. We do that. What is range do? Minus equal to 1. So I think they're doing 8. How is that one not encoded? If you're doing minus equals 1, oh yeah, that does make sense. Why is one not encoded? Y is labels. Note that y is not, and it can be computed as y or max access 1 from one not encoded if required. If that's really this yi minus pi, I swear to god I'm gonna go crazy. So this is the reason why. So here's the thing, even though like this like these differentials, man, this requires so much stuff. What the hell? So this stuff, I mean, come on, man, this is not even a good, well formatted document. How am I even gonna understand it? You know what? I don't care. I think we're just gonna implement this one. Now, correct me if I'm wrong, but if the output of this, the derivative that was just pi minus yi, um, you know what? I'm just gonna do that. Pi minus yi. So, yeah, you know what? I'm just gonna do that. And we can just take in like uh, probabilities and actual. You know what? Let's just use y hat and y. So we can just do return y minus y hat. This is a doubt, so I'm just gonna do like to do clarify. Now this clarify I will do off stream, not on stream, because I don't know how long it's gonna take me. I don't know how much help it will take me. I'm pretty sure it's gonna take me a good amount of help, so I'm gonna need like people helping me out with this, and so I'm gonna do this thing off stream. Till then, this is cross entropy. Have fun. So as you can see, this is just 126 lines of code, but as you can see, this is pretty complicated code. And you know, if you guys want, you can put it up into the testing module, get the loss. If you guys, so if we want to do that, we can just go ahead and do we can do loss is equals to categorical Actually, was it categorical cross entropy or was it just cross entropy? Cross entropy. Cross entropy. And we can just do loss dot forward on the y hat. What was y? Y was actual, y was predicted. Alright, cool. So y will be output 2 and y. Um, no, it was y in small letters. Just checking. Y is the predicted and y is actual. So we do that, and we can just go ahead and print it out. And let's run this. I think it will take me a little more time since I'm streaming. But yeah, let's have a check on the live chat. Oh, alright. Can't hear you, sorry, wow, you look so good. Alright. Uh, please give shout out. Shout out. Can you speak louder? Cause a lot of. Alright. Uh, and obviously, whatever, half of the things written over there were inappropriate, but I can't expect anything less from my sister, so yeah. Couldn't broadcast shapes. 300 by 1000 and 300. For what? I think it's for that one. Alright, we gotta transpose it. Not a big issue. We can just put in like a transpose. I know, like the framework that we are developing at this point, it is so, like, it's so subjective to the network that we are developing. I don't even know if it's gonna work for like a generalized network. So yeah. Also, is she still on the stream? I don't know. Also, let me get the timestamp for this. I'm gonna remind her that I gave her her shout out. So yeah, shout out. Also, thank you. I do look very good. RC. This is R. I don't think we need the transpose. Well, what do we do then? We obviously need to do that. So what should the shapes be if we are doing that? Let's have a look. So if it is 2 by 2, the rows of the first matrix should be equal to, so this should be, I think, 1 by 2, I'm pretty sure. Should it be 1 by 2? RC, yep. P dot. Well, that worked. Why wasn't that working then? I was actually questioning the math that I knew when I saw that error. Could not broadcast shapes. Let's test it again. Let's get like, I think I know what the issue is, but yeah. I'm gonna get the shape of the output. And we can also just do y is equals to y np dot reshape y to a 1 and 300. Just do that. This should work. This takes a lot of time to run. I wasn't expecting this much of time. Seriously, if you want to develop anything complex, don't even think about using this. Processing speed is like 20 times worse than Python. Could not broadcast shapes. Oops. No, that's not right. The rows of the first should match that. How the hell is that not correct? So is it for the sum? Is it for what? Wait, I wanna test this. I'm gonna test this out. We take this piece of code. Now let's test. Oh cool, we have a viewer right now. That's neat. Alright, so the issue is in here. At least I was able to narrow it down. If I do a transpose, does that work? Negative infinity? Are you kidding me? What the hell is this? Yeah, cool. Look at our loss. That's such a good loss. A loss of infinity. Yeah, that is not correct. And I'm pretty sure I know why that's the case. Basically, we have y hat and we are doing y times y. We're not doing log that. I think we have a couple of negative values in there. I think that's the case. Otherwise, this should not be happening. We shouldn't be getting negative infinities in our calculation. I think this is more of like a problem with the data rather than the actual network. So if we go ahead and print out the y, actually I'm gonna do it here. I'm gonna do that here. At least we don't have an error. That's good. I know this is not the output we are looking for, but at least we don't have an error. We shouldn't be having these negative infinities. Just a couple of zeros. Alright, we got the error. It's a couple of zeros. We gotta one hot encode this stuff, I think. Alright, so here's the thing. We know the issue. We have a couple of zeros in here. That's the reason why we are only getting negative infinities up to the number of zeros. And then we don't have the negative infinities. So if we can figure out a way to get rid of these zeros, or basically deal with these zeros in a way, that would be good. Basically I think one way I can deal with this is, if cal is equals to negative infinity, cal equals negative infinity 0. I know that's not right, but is negative infinity even a word? Do I have to do like math dot negative infinity, something like that? Because I gotta deal with those zeros. Alright, you know what, I'm gonna this is not that great. I mean, like, alright, now I'm gonna fix this off stream. I seriously don't know how to fix it. I'll fix this off stream. At least kind of sort of have the code in place, and yeah, so I'm gonna fix this off stream, and then I'll just have another stream maybe tomorrow, day after tomorrow, something like that, and I'll just explain to you the things. So that's it for this video. I hope you enjoyed it. If you did, like, subscribe, comment down below what else you want to see, and until the next time we meet, bye bye.